Okay, so for this video, it's going to be about substitution. Mostly going to be about a few more examples. So the idea here is if you're going to take the integral of f of some g of x, okay, then typically what you're going to say is that you let u equal that inside function. Now, once in a while, it's not going to be obvious who the inside function and who the outside function are. But in this case, when it's written like this, it's pretty obvious to see. And of course, du is going to be g prime of x dx. And then just look, you're going to look to replace this with f of u and then du. Now, to do that, there may have to be a constant you divide over. It could be a variety of different things. So the one we did in class today, I think to start off with, was something like cosine of 2x minus 7 or something. Well, there's your inside function, so let u equal that inside function. So then du would be 2 dx. So then a half of a du would equal a dx. Okay, so I'm going to have the cosine of now u. And I want to put dx right here. Well, there it is. Dx is a half of a du. So from whence did cosine come? It came from sine. Okay, and this is how I do it personally most of the time. And then I just remember to, oh yeah, gotta resubstitute because this is an indefinite integral. That is just an antiderivative. So one like this guy will come up. Now this guy, if you think about it, x minus 7 has just been shifted over to the right 7 units. Boom. So now it should have the same exact slope as square root of x, just should happen further over. So the idea here is, alright, let u equal x minus 7. The derivative of u is du, the derivative of this is just dx. So in other words, u and x are one-to-one functions. The only difference is where they show up. So I'm going to have the integral of u to the 1/2 du, which of course is going to be u to the 3/2 and then 2/3. Like so, or if you prefer 2/3, not you idiot, x minus 7, there we go, to the 3/2. Okay? So again, this case here, because it was just 1x, and the u and the x are changing in the same rate, we've just slid it over. So the slopes will be the same, they just occur at different locations. So this one here looks very similar, except that now there's an x out front, and you're like, oh, cool. Then u is going to be equal to x squared plus 3, because it's the only function that's really inside a function. That's how I do it. And then it's 2x dx. So I see u to the 1/2 right there. That's easy. Oh, wait a minute. I see x dx. Well, there's x dx. Again, that's a half of a du is equal to an x dx. And so we just did this problem basically a second ago. Almost. And so it's a third x squared plus 3 to the 3/2 plus c. Alright, so this one is going to look very similar and you're going to think it's exactly the same, but you're wrong. Actually, let's shake it up a little bit. Ooh, nice. So, pretty interesting here. And you say, well, let's let u equal this, of course. So du would be equal to -2 dx. Awesome. Well, so I've got u to the 1/2. That's easy. So dx is -1/2 of a du. Now, I apologize. Apparently, I'm stuck on halves and twos today for some reason. And so I'm going to replace this dx with -1/2 of a du. What about that guy? What the heck is x? If only there was an equation somewhere that we could solve for x. Oh, wait, there is. You could take this fella and solve for x. So if you play musical chairs, you get something like this. And then you get this is equal to this over that. Ta-da! And so then you could really do this. I'll write it two ways, first of all. You could do this first. You pull this 2 out front and get negative a quarter. Then you're going to get 3 minus u times u to the half du. What am I going to do with that? Well, here's what you're going to do. You're going to distribute. So you can get 3u to the half. Again, all I'm doing is multiplying here. I'm not doing anything else with it yet. Alright, now I can integrate. So, this is u to the 3 halves. There's still a 3 in front of it. So then 2/3. And then this is going to be u to the 5 halves. And then a 2/5. And then a plus c on the end. So this is 2 u to the 3 halves minus 2/5 u to the 5 halves. And then so you're going to get negative a half of a u to the 3 halves. And then minus plus actually a 10th. Isn't that right? A 10th? I think. U to the 5 halves plus c. And then of course we need to stick it back in, so our u is 3 minus 2x. So there's a couple ways to write this problem. You could write it like that I'm doing right here. This is 2x. They also have a half in common. They also have 3 halves in common. So you could pull that out. You can do a number of things. What always cracks me up is when your book does weird stuff like this. Like, I know, let's pull a 1/10. A 1/10. A negative 1/10. Yeah, let's do that. Out of both of them. And while we're at it, let's pull out a 3 minus 2x to the 5 halves out of both of them. Awesome. Wait, what? So, what's negative a half divided by negative a 1/10? Alright, well, it turns out it's 5. Right? So, a half divided by a 1/10. This means the invert multiply. Yep, it's 5. Wait a minute. I took 5 halves out of this guy. Well, that's strange. Actually, your book would have done that. They would have taken out 3 halves. And they would have gotten, well, just 5, because this would have gone out. Okay, well, if you take 1/10 out of this, you're going to get minus because it's a negative. And then you're going to end up with 3 minus 2x to the 2's power, right? Which is to the first power. And then they'll distribute that through, and you're going to get 5 minus 3 is 2, plus 2x. Anyway, the reason I show that is because your book is notorious for doing stuff like this. And what I would do is I would just graph that to see if it matched up with what I got, and see if I'm in the right ballpark. If I had a TI-89, I might actually set them equal to each other and hit solve, or set them equal to each other and see if in fact it says true. I'll show that in a minute. Alright, so the way I would probably check it, the easiest way to do it would be to use the graphing calculator. So I graphed them both. As you can see, they're right on top of one another. Maybe you can. Yeah, there you go. Boom. That's the easiest way to check. So if you get an answer that's different in the back of the book, that's the fastest, easiest way to do it. So yeah. I think the other one's probably the hardest to get a handle on is when you have something like this. You know, and then, yeah. Oh, and don't panic if the dx is on top. They may do that just to see if you're paying attention. But you may or may not be, and that's fine too. Anyway, so again, this is probably the hardest one to see, is because really there's a function that's 1 over x. Do you see it? And so there's a function inside of that guy, and then part of its derivative is in that numerator. So I think we did one like this in class, but I'll just do another one just for fun. So again, u equals 3x squared plus 5. And then du is equal to 6x dx. So 1/6 dx, or du rather, is equal to x dx. Probably had to pull that 5 out front to make it look prettier if you did. So that's 5/6. And a little du action, and then 1 over u. Okay, and then you could either do it this way, and so you're gonna get 5/6 ln of, and then go ahead and resubstitute. So it's 1/2. It's the ln of u. Notice that I don't need the absolute value this time in essence because 3x squared plus 5 is always positive. But a good idea is to get in the habit of putting them on there. And that's how it's technically supposed to be. And then plug that 2 into 5 in. So you're going to get 5/6, and then you're going to get the ln of 80 minus 17. Oops, the ln of 17. There we go. Something along those lines. Okay. Now the other way to do that, of course, is to take these two dudes, which are x's, plug them into here, and get u's out the other side. So of course, you plug them in, you're going to get u is 80, and you're going to get u is 17. So right here, notice how I didn't put the x's on here, but if you did it in terms of u's, you could have just done this. The difference being is you don't put that in there anymore. You leave it just u, and then now you plug it in, and you get 80 and 17, and lo and behold, it's the same answer no matter how you slice it. So substitution's pretty easy to do. Again, it's basically undoing a chain rule problem. So you should see the resemblance as you're doing them, I hope. And good luck to you. Somewhere, dang thing.